All right, it's a short unit, Unit 4 is, and so on today's show, we close up the unit with a look at the trapezoidal rule for approximating integrals. Today is the day where we say, rectangles, you've been nice, but trapezoids, you might be better. Let me show you what I mean. Let's consider some generic function on some closed interval a to b. This is y equals f of x on some closed interval from a to b. And the thought is we're going to partition this interval into a bunch of subintervals as we have before. But instead of using rectangles to approximate the area, we're going to take all of these y values, all of these points on the curve, and we're going to connect them with straight lines. And if we connect them with straight lines, then the shapes that we get are trapezoids. They're not the familiar looking trapezoids. They're like trapezoids on their sides, but they're all trapezoids. And I know how to find the area of a trapezoid. The area of a trapezoid is 1/2 the height times the sum of the bases. And so if I ask you for a trapezoidal approximation, then all you have to do is connect a bunch of dots with straight lines and find the areas of trapezoids using the formula h over 2 times base 1 plus base 2. Now, if all the delta x's are equal, then some nice stuff happens. Then the trapezoidal approximation is the following. The delta x's would all be the same, and they would be the heights of our trapezoids. So the height of the trapezoid would be delta x for every trapezoid. Then, what are the bases of the first trapezoid? The bases of the first trapezoid are this y value and this y value. What are the bases of the second trapezoid? The bases of the second trapezoid are this y value and this y value. What are the bases of the third trapezoid? This y value and this y value. And so what ends up happening? You get f of a plus 2f of x1 plus, and then everybody in the middle gets doubled until the very end, and we've got f of b at the very end. All the ones in the middle, all the y values in the middle are used as a bottom base and then as a top base. So all of the y values in the middle get doubled. Whereas the f of a and the f of b are only used once as a base. Let me show you what I mean. Oh, one more thing. If you don't like this formula, and that's totally fine, the trapezoidal approximation is the average of the left endpoint and the right endpoint approximations. And I'll show you why that's true. The left endpoint for a particular rectangle would look something like this. This would be the left endpoint rectangle approximation. But the right endpoint would look like this. And I think it's pretty obvious that the blue line splits that difference in half. And that's exactly what finding an average is. So it's pretty straightforward. The trapezoidal approximation is the average of the left endpoint and the right endpoint. So let me show you what I mean with a very straightforward function. I want to use a very basic function. I want to use cosine x plus 1. cosine x plus 1, and that looks like this. On 0 to pi. I want to use it on 0 to pi. You know what? I'll even move this guy up, and I'll let this be cosine x plus 2 on 0 to pi. And I'm going to say, let's estimate the integral from 0 to pi of cosine x plus 2 dx using a trapezoidal approximation with 4 subintervals. 4 subintervals, which means we've got to know where our middle is, we've got to know what the middle of that is, we've got to know what the middle of that is, and we're going to utilize our trapezoidal approximation. So how does that go? We're going to take the delta x over 2, delta x over 2 times the first y value plus 2 times the second plus 2 times the third plus 2 times the fourth plus the last. And then all I have to do is know what the cosine of pi over 4 is. This should be fun. Cosine of pi over 4 is radical 2 over 2. And then the cosine of 3 pi over 4, that would be negative radical 2 over 2. And then the cosine of pi over 2, well, that's straightforward. And so what do we end up with? We end up with pi over 8 times 3, 7, 11, 15, 16. 2 pi? But more importantly than the arithmetic is the idea that we've got delta x over 2 times first, last, and then 2 of everybody in the middle. That is a key. One more. One more. We're actually almost done. Let's do, this is y equals 1 over x squared, and it's 1 over x squared. Let's do it from 1 to 2. And let's estimate the integral from 1 to 2 of 1 over x squared dx with a trapezoidal rule with 4 subintervals. Trapezoidal rule with 4 subintervals. So what have I got here? We're going to break this up. This is 3/2. This is 5/4. This is 7/4. And so what are we going to do? We're going to take the delta x over 2 times first y value, 2 of the second, 2 of the third, 2 of the fourth, last y value. So let's see, 5/4 squared is 25/16. 3/2 squared is 9/4. 7/4 squared is 49/16 plus 1/4. Time to get a look at what this actually is. So we pull out our calculator, which probably should have been up already, but I know you've got 15 seconds to wait. You're not doing anything. And we say that this is 1/8 times 1 plus 32/25 plus 8/9 plus 32/49 plus 1/4. And we add them all up. And divide by 8. And that's approximately, take a picture, 0.509. Right? So now the question is, how close did we come? How close did we come? Well, if we were to actually integrate 1 over x squared from 1 to 2, we would get 0.5. And that just begs the question. That just begs the question. How did we know we were going to get an overestimate? How did we know that when we connected the dots with straight lines, we were going to get a little bit more? What is it about the function? I'll give you a hint. It has to do with, wait, hit the pause button and think about that. Hit the pause button and think about why we got more. Is it because the function was decreasing, or is it because the function was concave up? It's because the function was concave up. When you have a concave up function, the trapezoidal approximation will be an overestimate. Not by much, but an overestimate nonetheless. Okay, cool. That's the trapezoidal rule. You've got to know how to execute it. You will know how to execute it. Fantastic. We'll see you tomorrow.